So good evening, everyone. Today we'll be having the homework for P2 bootcamp. And as all of you have gone through the write-up now, we believe that you have gone through the write-up by now. We all know that the homework is about uh, doing a task where we are trying to recognize the speech and convert the speech to its transcript. So we'll be implementing a attention-based end-to-end speech-to-text deep neural network in this homework. And the difference from the other homeworks in this homework will be that we'll have an attention module or like an attender that will actually be like the context to a language model. So you might notice that how is this different from like the 3P2 homework or the 4P1 homework? Or is this homework really different from homework 1P2, where we are also doing like a character-based recognition, but on a frame level basis? So we'll be answering all such questions today, and we'll be going over through the homework piece by piece and module by module. And then we'll also go over the write-up and the handout, and then we'll finish this bootcamp by answering some questions that you guys have. So in this whole model flow diagram, we see that the listener has been already done in homework 3P2. So yay, we don't need to do that, or do we? So we don't really need to make another listener or an encoder. We'll be taking our encoder from the 3P2, and you can also experiment with taking a pre-trained decoder, a pre-trained encoder, in fact, from a homework 3P2. We have seen that it works, but if you don't have the pre-trained weights, you can just start using the coded encoder. And then what about the speller? The speller is done in homework 4P1. What does that mean? That means that before you start with homework for P2, it makes it kind of beneficial for you to complete homework for P1 so that you don't have to rewrite your speller. And you would wonder that, okay, we can just write a speller in homework for P2 and then copy it to homework for P1. But that is kind of the other way around. And because we have designed the homework for P1 in such a way that it will help you set up your speller easily, we have provided more informations on the things that are required to make you your speller. And also the homework for P1 speller is without the attention context, which means that it is much simpler to code. And it also doesn't have teacher forcing. So those are the two extra things that we'll be talking about in this bootcamp today. And let's move forward about like talking more about the encoder and decoder and what you can experiment with them. So as we have seen in the previous homeworks, encoders are feature encoding modules that encode a speech into feature vectors, or like encoding vector space, right? And these feature vectors are derived from the input sequence of speech, like speech sequences. These speech vectors are like strong structural continuity with adjacent vectors, as well as long-term contextual dependencies. And we generally use like convolutional neural networks and RNNs for encoders, which we have already seen in 3P2. So the important factor about 4P2 encoder is that you may or may not have used PBLSTMs in homework 3P2, but in this homework, we have seen that it is really compulsory to like, it's basically, we were not able to train a model without a PBLSTM for this homework. So it is like really like it is hardly suggest like it is suggested that you use these PBLSTM modules if you didn't code them in your 3P2 homework. And about the decoder, I found this very good line of what a language model is. And it just said that a language model is a probability distribution over words or word sequences. So the model basically learns how to set up like words so that it makes sense. And that is what we have given in the write-up for homework for P1. And if you want to know more about what a language model is or what like a decoder is, it is extensively covered in the homework for P1 write-up. So there are a lot of things given in 4P1 write-up that talk like that go over all the ways that the probabilities of these different words are calculated. And it basically has a pseudocode as well as like all the logical aspects to a decoder in that write-up. So in this homework, we kind of give a context to the decoder, and this context is basically what the attention module will calculate. So this context is basically derived from the encoder, and we'll go over like some few more slides to understand how this context is being derived. And if the context is not derived correctly, then the decoder will not function very well. So stating this again, it is very important for you guys to finish homework for P1 first and then start with the P2 homework. Okay, so coming to attention, what is attention? We have seen attention a lot, many times by now. We have seen it in classes, lectures. We have also specified specific lectures in the write-up. I think it's lecture 17 and 18, right? And so what attention is basically doing, it's an output, it's relating an output character to the input vectors feature spaces. And we kind of make a query out of each character, as Abu suggested, that you can look at as a database perspective, where you fire a query, calculate all the keys, and then return the values. So we make a query out of the character, we multiply it with the keys to understand what needs to be retrieved. And after that, these retrieved keys are used to calculate how much weights are to be allotted to each of the values. And finally, we do a weighted sum of these values to find our attention context. So we will see how this attention context becomes important, and why is really attention important. Like, can you somehow relate it with the 1P2 homework, where we were also using something like a context to calculate the frame-wise character? So as you see, this is like an attention diagonal, and you will see how, like, when you will solve the homework, you will kind of make such an attention diagonal. And what this diagonal basically says is it tells you how, so this side, the y-axis is the speech axis, which tells you the sequence of speech. So it's the time sequence, like time steps of each speech sequence. And on the x-axis, we have the transcripts. So it's input versus output. And it basically shows you how the first, the 0 time step is related with the 0 speech vector or something like that. And similarly, you can basically think of it in terms of that, if I want to actually like say out some speech or like say out an audio, and you would want to manually like curate which part of my speech corresponds to which part of the sentence, you would make like a diagonal. It would look like a diagonal. And how we can understand this diagonal is, this is actually the attention weights that we will get when our attention module will work correctly. And if we see that, so here each column, if you see, is something like this. So I just like cropped the 6th column of this chart, and we can just see that if 6th character was our query, the attention module would have given us attention weights, something like this. So what does this actually like say? It basically just says that you have to, okay, so the 0 to 34 will be our encoder feature sequences. So like these will be the sequence of our encoder features. And the attention weights basically just say that you have to focus more on the 8th encoder sequence and a little on the like 7th and the 9th encoder feature, right? And we can also see another example where we take the 20 as a query, and it says that focus on the 19th and the 20th encoder sequence. So like you might also like think, why are we using such a complicated system to calculate this context when it is always going to be very similar to, like, if we are giving it 20, it is just predicting something like 19 or 20. Why are we doing such complicated thing to just calculate the context? This context is very similar to something that we were doing in 1P2, where we were just taking the time steps that were before and after the frame that we were trying to predict, right? So we are doing this complicated systems because the attention diagonal will not always be a diagonal. So as you see how, like, the once the sequence lengths start getting more and more, you'll realize that the attention diagonals are not often diagonals, because you will have some pauses in the like pauses in the audio signal, and the speech will like dip for that particular sequence. And that is where we want the attention to be smart enough to recognize which part is to be focused, right? So that is why we can't just set a diagonal for all of these things. And that's why, like, some of you also observed that the context was hurting some of, like, the context was in fact hurting some of your performance in homework 1P2, where it was kind of making it difficult for your model to differentiate between, like, the transition of letters. So this is how the attention module will actually help you kind of figure out which part of the speech you are supposed to focus for each of the output characters. So this is basically like a small intuition of the attention and how we will be like plotting the attention plots. If your attention plots are coming something like a diagonal like this, it means that your attention module is working correctly. And you will be like trying your attention diagonals over the toy dataset first to make sure that your model is working correctly. If your attention diagonal is like showing up on the toy dataset, it basically means that your model is working fine. It's training fine and it's learning fine. If it's not learning the attention diagonal on the toy dataset, then you will need to go back and look at your model and try to understand which part of code is not working for you. And to make this homework simpler, that's why we have kind of given you the encoder in homework 3P2. And if you're like solving the 3P2 correctly, it means that your encoder is basically right. If you're solving the 4P1 correctly, it means that your decoder is fine. So that just gives you the attention mechanism and the teacher forcing thing to, like, the teacher forcing network to basically like align properly. And the whole task will be to just make sure that all the moving parts are set correctly to this attention diagonal to like show up magically. So after this, I'll give the stage to Vish and he'll continue from here.
Right. So right now, I think the way we're going to go forward, not a lot of people are in the boot camp. So, but either way, that I think that kind of makes it a little easier as well. But um, assuming that you guys have gone through the write-up as well as the starter notebook, I'm sure you might still have questions. So we kind of want to go through the starter notebook while it's going to be kind of a Q&A session where you can feel free to ask questions on any kind of portions that you don't understand, um, either relating the write-up to the notebook or relating the notebook to the write-up or vice versa, right? So feel free to like pause me or like interrupt me and ask me questions, whether it's using your mic on Zoom or basically in chat. And yeah, don't feel like any question is stupid here or silly. Like even the silliest of questions can be still entertained, because this homework has a lot of moving parts. So the goal would be to try and ensure that you understand each part correctly so that you know where to look when things are not working, because that's really important. A lot of students just struggle not knowing how to debug or what am I supposed to look at, where is it going wrong, because there's so many things that are moving. So the goal would be for you to definitely get a deep understanding of how each module connects to one another so that you know what's going wrong or you know where to debug, right? Um, anyway, let's see if I can share my screen. Uh, right. So this is the starter notebook. You guys would have already seen it. The biggest reason we gave you the toy data set first is, like Varun said, it's much easier to just get things running with the toy data set to check if you're getting the diagonal. If you're trying to run things, or when you complete your modules and you're trying to run it on the main data set, it typically takes a good amount of epochs to converge, and training takes time. It doesn't take, just less than 30 seconds. So the reason why we give you the toy data set is because it has small sequences, it has fixed length sequences, so you don't have to worry about variable lengths. And it is also in line with what you guys did from 3P2. So like it won't exactly be something new that you're dealing with. It's still phonemes, right? But you can still do an attention like a mechanism on a similar type of data set with phonemes. And that's kind of why we gave you the toy data set. It's been fully coded. You don't have to change anything here, right? Uh, Nothing has to be changed with respect to the toy data set. And as you can see, it's basically 16,000 MFCCs that we've given you. Okay, I see a question. Why do we use EOS token toy instead of pad token toy for padding? Right, you can use either SOS, EOS, or pad token. Right here, the way it's been implemented is using an EOS token, but typically pad token just makes it kind of straightforward, so you know that it's a pad token. It doesn't matter what value you use, right? As long as you make sure that while decoding, you remove that value for padding, right? In the case of the way if you've read the write-up, when you want to basically ignore padding values associated with your vectors or your predictions, we recommended you use ignore index in cross entropy loss, right? So whatever you use for padding, you want to ignore that specific token while you're computing your loss. So you set that token as ignore for the ignore index parameter in your loss. Um, any other questions regarding the toy data set? Yeah, just make sure that you ignore the one that you're using for padding. It's just this is kind of how it's a good catch. Probably it's worth changing it to pad token just to keep it consistent. But this is kind of how we were given the toy data set before by the one who coded it, was Joseph. Um, but yeah, it doesn't matter what you use. It's just convention. Make sure you just ignore it when you're computing the loss or whatever you need to ignore padding. Sometimes you also, in some situations, like when you're implementing a transformer, you might also want to remove padding, and you might also want to mask future indices. So you might have to create manual masks. So when you're creating manual masks in those situations, you have to make sure that you ignore the right values, basically. Anyway, that's the toy data set. And then this portion is for you to just use your Libri speech data set that you've always implemented for 1P2 and 3P2. This is going to be extremely similar to 3P2. The only change being the transcripts are going to be alphabets instead of phonemes. So you can literally use the exact same data set, except right here, you're going to be using this list to encode your transcripts instead of a phoneme map, no CMU dict alphabet stuff, because we're not dealing with phonemes, we're dealing with alphabets, right? And for some people who might be asking or wondering, why don't we, use, like, why don't we follow what we did in 4P1? Why don't we transcribe words? Why do we transcribe characters, right? That's a natural question to have if you're coming from 4P1, because we asked you to do a word level language model there. The reason we don't do that here is because transcribing words comes with a few drawbacks. One being, if you have words that are in your training data set but not in your test data set, if the difference of that is large, now your model has to classify them as unknown tokens, because you need to have a token when your model doesn't know what the specific token you're predicting is at that time step. And when the difference of the number of words between your training vocabulary and your validation or your test vocabulary is large, your model is not going to perform really well, as opposed to a character level model. But there are challenges with a character level model too, right? Because it doesn't understand what are the common words in the, in an English probability distribution that you had model in a language model. So there are drawbacks, but then basically this model can predict rarer sentences or rarer words. But if you're using a word-based approach, then you might have to deal with unknown vocabulary, right, that your model might not know, and then that might drop your performance. You could explore both if you wanted to, but we recommend a character level model because that's that based on our experiments, uh, isn't it intuitive to recognize phonemes rather than characters/words? What exactly do you mean by intuitive? Uh, it really depends on the task, doesn't it? Some people might want to do um, uh, direct, like automatic speech recognition just to classify what you're speaking rather than trying to understand. Speech is made of phonemes, yes, correct? Okay. It is made of phonemes, but it depends on the task you're working with. People can't really read phonemes out loud easily, right? But you can read English. Might be recognizing phonemes might be easier for the model. Well, speech is made of signals, right? If you think about it, phonemes is what the transcript is that you're trying to classify. So at the end of the day, it's basically trying to see if your model can associate the signal with what you're trying to predict. And at that point, it's basically replacing your vocabulary, right? You're replacing your vocabulary with phonemes. Here, you're replacing it with alphabets. At the end of the day, it's basically trying to understand what the signal means in terms of English or in phonemes. So I don't think it's, I don't think it makes a big difference in terms of what's more intuitive. But yeah, good question. Anyway, so that's basically your vocabulary right here. You can implement it the exact same way. Just make sure you use the vocabulary to encode your transcripts and the pad token to use your padding when you're padding your sequences. This, by the way, just so people don't get confused, these are outputs from loading your data in your dataset class. So you might want to include print statements in your dataset class when you're loading your dataset, right? When you're appending your MFCCs, when you're loading it from NumPy one by one, you can have like a MFCC length list and then find out the maximum length of that. That's basically your max MFCC length. And then you can find out the average by taking the mean of that list, right? Then do the same for the transcripts. So that's kind of what this is. This isn't coming from your data loader. We're not really asking you to implement a custom method for your data loader that does anything like this. This is a pure.
Yeah. So one thing I wanted to point out was that in the 3P2 dataset, we actually trim off the SOS and EOS characters. But in this homework, because we need like a start of sentence signal and an end of sentence signal, that's why we will not be trimming that part. And that's like a minute difference that might change like your training cycle. That could be like a very small thing that you would never like,
right.
Yeah, see.
And you might ask why we do that. And if you've read the homework for P1 write-up, we explain why we use SOS and EOS when we're doing sequence modeling. Sequence modeling, sequence to sequence, basically is different from CTC, right? You have one probability distribution, but here you're trying to generate one probability, like a probability distribution for sampling every token auto-regressively, right? That's different from what CTC is. So the reason why we need an SOS and EOS is we need to know when to stop that autoregressive modeling, if that makes sense, right? We can't keep doing that for like infinitely. So we need to know at what point does the model decide that, oh, this is what the transcript is, let's stop here. And similarly, the model needs to know when to start. So we have a start of sentence token. That's why we have the SOS and EOS tokens. And they will be used here more than anything. So we also ask you to use it in homework for P1, but then, so you would be using it in both areas, basically, SOS and EOS. But I think in homework for P1, we ask you not to draw from SOS and EOS because the way you do your decoding there doesn't involve you stopping when you're encountering EOS. We ask you to generate it for a fixed number of time steps instead. But here you will have to basically model your sequence until you encounter an EOS, if that makes sense. Let's go ahead to the model. Right, this is the listen, attend, and spell model. There's a paper on this. We've tried to follow the exact same architecture that they have followed in the paper. The one difference being the attention that you might find in the paper and the one you might find here, we're using query keys and values, right? They might not be doing that in the paper because the query key and value approach was outlined in the transformers paper that came later. So That's a difference for anybody who gets confused. Why are we using query key and value here, but the LAS paper isn't? We're using query keys and values because the transformer paper innovated on it. And then that's kind of why we're trying to use the same attention approach here. So the listener is basically the same thing that you have implemented in 3P2. So there's not much to go over here. Like Varun said, you want to basically ensure that you use PPLSTMs, because based on our experiments, you will need PPLSTMs if you want to perform really well for this homework. Attention, right? There are different types of attention. What we have basically gone with is the query key value scale dot product attention. There's multiple types of attention that we've also mentioned here, including multi-head attention, right? But if you choose to go this route, do know that the TAs, or mostly all TAs, have implemented mostly number one, right? These are guiding pointers given to you if you want to experiment with different types of attention, but we've mostly experimented with one. Some TAs might have experimented with 5. So that's basically it. Yeah, the attention class, the pseudocode has been given here. It's been explained thoroughly in the write-up. Do you guys have any questions about attention from reading the write-up that you don't understand? You can ask questions about the write-up as well right now. By the way, if you do have anything, feel free to put it in the chat about the write-up. You can refer to the section and we have the write-up right here. We can go to that section and we can clarify. The write-up is pretty huge. Can we use attention that was in the LAS model? Yeah, you can feel free to use. Basically, I think linear attention. I'm not sure what they use, but you can feel free to use, and if that works really well for you, awesome. We don't really restrict your approaches here, what you want to use, as long as you're using some form of attention.
Hi, I had a question about I think in the write-up it mentioned something about beam decoder.
Right.
I was wondering, it said like you could either do beam decoder or something else. I was a little confused about that part.
So okay, let's go over the inference section here. So you have 3 ways of basically understanding. This is also covered in, or at least a portion of it is covered in homework 4P1. But the idea is you have 3 ways to understand what is the next most likely token or character that you're going to model. One is the greedy search, which is just going to basically get the most likely at every time step. The other one is a random search, where you're basically going to do some form of random sampling, right? Not exactly finding the most likely output each time, but using some form of random sampling. And we've outlined this in the appendix, but in practice, what you're doing is you're generating several of these random samples, basically several hypotheses, right? You're not just doing it once. In a greedy decoder, you're just going to decode once. You're going to be like, okay, what's the most likely at each time step? Just going to append those characters while you're decoding and just go ahead and tell you what the most likely sequence is, right? Or most likely hypothesis sequences. For random sampling, you're just going to randomly sample these tokens at each time step, but you're going to do a bunch of them, right? And you're going to run these multiple times, and then basically choose the decode that has the largest probability, basically, or the product of probabilities, or you can say the log of the probabilities as well, if you're choosing to use the sum of the probabilities. Beam search is similar to how we did things, or at least the idea or the concept is similar to how we explained it for homework 3, or how the prof explained it. But the way you implement it is where things get a little tricky in homework 4. Why? Because basically what you're doing now, you're not dealing with a fixed probability distribution for all time steps like you did in CTC, right? You had log probabilities for all the time steps available right at the output. Here, the difference is every output or every time step, right? Output at every time step depends on the previous one. So you don't have the entire probability distribution available to you when you start your decoding, right? At every time step, you're supposed to consider, oh, what is my best likely path to take in your beam search? So your beam search is going to become a part of your forward or inference, right? If that makes sense. So that's where things get tricky with respect to beam search. The difference between how beam search you might have done in, like how you might have done beam search in homework 3 as opposed to homework 4 is the fact that here you're going to explore k beams at every time step and then find out what to choose, right? And then explore 3 from there, like 3 from there, if that makes sense. You're going to continue exploring k-beams at every time step, and then choosing the hypothesis that has the largest log probability sum or the product of the probabilities. Typically, we work with the sum of log probabilities because we want to avoid underflow. So let me just say you work with sum of log probabilities. Whichever has the most likely probability is what you're going to choose. Pseudocode for this, we've given it to you in the appendix. So if you scroll all the way right here, yeah, we've given you some pointers on random search, right? And the pseudocode is right here. Explaining this would require me to basically go over how the speller works. But basically what you're going to do is you're going to loop over your time steps, right? When you're looping over your time steps, you're basically doing the LSTM step at each time step, right? But you're maintaining a paths list at each time step. Why? Because you have to loop over all these paths. That's the point here. So rather than just having one loop and then fetching the most likely character at each time step, now you're going to loop over a set of hypotheses at each time step because you have to explore k hypotheses. So that's the difference. And you're going to check if the path has encountered EOS. If it has, you end the sequence there and then append it to the list of paths. Otherwise, basically what you're doing is you're going to get the top k paths, right, at every time step. So you might have decoded one for the first one, second one, and then when you're at the third time step, you might have 3 different paths here, and you're going to get the top k paths, and then you're going to loop over those specific, like for these candidate paths, what possible symbol is going to give you the maximum probability, right? So what possible symbol, if used for those 3 paths, is going to give you the maximum probability for those sequence, and then you're going to use that path. You repeat this for basically every time step, so it's a little more involved, if that makes sense. And then here, once you find these paths, you can basically prune those by selecting the top k from that basically all that path lists you've done for calculating the probabilities of 31, 30. Yeah, you have 30 symbols. So if you have 30 symbols, you're going to get 30 paths here, possible paths. So you're going to decide what to keep when you prune right here. It's a little involved. I'm sure you might not have understood everything in what I just explained, but I hope the overall idea kind of makes sense. Does it make sense? Or do you want me to go over it again?
That makes sense. Thank you.
Right. We don't recommend you implement beam search right away because it takes too much time, or it's more involved in the fact that you have to really debug quite a few things. You might not get it right at the first step. You might be spending a lot of time. Instead, we recommend you implement greedy search. It's the most straightforward way to do things. Just take the argmax and find out what's the most likely token at each time step. Go ahead with that. Make sure everything is working with greedy search, and then get like greedy search is sufficient for you like to reach the cutoffs. So beam search is just going to give you an improvement beyond that, right? So don't worry too much about beam search unless you really are aiming for, getting a really crazy cutoff beyond the high cutoff. So
Yeah.
why can't we use CTC beam? Because this task is not CTC. Like I just said, you don't have a fixed probability distribution for all time steps, right? Your probability distributions change at every time step because it's dependent on the previous time step. You're using attention context, to basically go over every time step. So because we have that dependence, that autoregressive dependence, you can't really use CTC beam decoder for this. That's kind of why we have to brute force, or like not brute, I wouldn't say brute force, but basically implement the beam search in your forward for inference. So you'd have a separate function for inference as a part of your model. Anyway, good questions. 4.3.2. Where is that? 4.3.2. Right, cross entropy loss. Right here, this is pseudocode. You can literally just call nn.cross entropy loss. You don't really have to go worry about this, which is why we also tell you that this doesn't exactly translate to code because you have PyTorch modules for things. But what you're doing here is that basically, would you mind telling me what you don't understand? Is it the padding part? The padding part, all you need to do is set the ignore index parameter to the pad token, and basically the loss ignores all the loss values corresponding to the padding, so that you don't have to mask your vectors manually. PyTorch has that functionality, so it's handy. But basically what you're doing here is, yeah, and the reshape part, I hope that's kind of straightforward, because you're going to have a 3D array, right? Arrays of probability distributions, but you'll have to compare it with your labels. So you'll just have to reshape it like you do for homework 4P1. Would my training time be affected by greedy or beam search? Yes, of course. And by the way, the idea is to never use beam search while training, by the way. Yeah, so technically, no, your training time won't be affected by beam search. Your inference time will be affected by beam or greedy search, right? So beam search is obviously going to take a longer time than greedy search. But yeah, I would recommend just doing it for the test data set. I wouldn't be doing it for validation at all. So it's a one-time thing. And again, unless you clear the high cutoff, don't waste time on beam search. That would be my number one tip.
You can like actually train your whole model first, and once you're like satisfied with the greedy search model, you can just add a module to just do decoding on the fly. Because weights won't really change.
Exactly. Beam search is just an inference method, so nothing really changes. You can add it at any point in time. So you don't really have to worry about, oh, I have to have it during training. Yeah, anybody else have any other sections that they don't understand? Do people understand teacher forcing? Do you guys understand what it's doing, or why we are doing teacher forcing? Basically what we're doing, I'll explain it anyway so that it's kind of clear for people, because teacher forcing is critical for you to achieve convergence and get a good score. As you can see here, typically in this diagram right here, what we do is we pass the SOS sequence, we draw from the distributions at every time step, right? And we pass that as input to the next time step. We do not need teacher forcing for the earlier deadline, right? Yeah, you can just, you would still have to implement teacher forcing, but you wouldn't need a teacher force schedule. You would still need to understand what to use. Not exactly. The way I would say it is, you need to understand this diagram. Yeah, this diagram and this diagram to basically know what to pass to your model. Let me explain so that it probably makes a little bit more sense. So at each time step, what happens is you're drawing from your probability distribution, right? You're drawing a character and you're sending that as input to the next time step, right? You're sending an embedding of that in character. So you're drawing a specific token or a character at that output time step, and then you're taking the embedding of that character and then you're sending it to the input of the LSTM for the next time step, right? And basically, when you're training your model from scratch, these predictions are going to be garbage. Your model doesn't know what it's supposed to model in terms of language, what characters make sense, what doesn't make sense. It's not going to know anything, right? So these predictions are going to be garbage. So when you're going to feed garbage as input to your model again at the next time step, you can imagine learning is going to be terrible, right? So to account for that, we have this teacher forcing method that basically allows the model to cheat, right? Instead of relying on its own predictions early on, what we're doing is we're trying to tell the model what the correct prediction should be, right? And asking it to use that information to learn, to predict the correct things, right? And how much cheating you do is what's controlled by the teacher forcing ratio. If you have it as 1, right, you're basically saying that the model has to use what should actually be the transcript for that, or whatever should be drawn is the same as y of 0, right? You're saying the model should be using whatever the ground truth transcript is as input for the next time step, if that makes sense. We're also doing maximum likelihood estimation. Maximum likelihood estimation. For the speller part, I mean,
So
I wouldn't call it exactly maximum likelihood estimation, because it's not just the language model we're working with. But if it was just the speller, then yes, we would be doing maximum likelihood estimation in some sense. But we're not doing that, right? We're using the encoder um, um, encoder outputs, the attention context. So it's a little bit more sophisticated than just maximum. So we need to feed the correct target into the next time step. Correct target from the previous time step to the next time step as input to the next time step. Right? What should have actually been predicted, right? That's what goes into the next time step. Exactly, right? Teacher forcing is needed so that your model kind of learns what it's supposed to be doing instead of just, because the whole idea is that you're asking your model to rely on itself to learn in some sense, and it's going to do a bad job if you don't guide it. That's kind of why we use teacher forcing. Right. So all you have to do for that is basically sample a specific probability, right? If your teacher forcing is going to be ratio is going to be 1, it doesn't matter. Any sampled probability between 0 and 1 is always going to be less than 1. So it doesn't matter. But you sample a probability, you check if it's lesser than the teacher forcing ratio, right? If it is in fact, less than the teacher forcing ratio, is it correct? Am I saying it right? Less? Yeah, if it is in fact less, then you end up basically using the ground truth embedding, right? The characters, ground truth characters embedding as input to your model. Again, ground truth character that was supposed to be predicted from the previous time step, right? You don't want to use the ground truth character that's supposed to be predicted for the current time step, because that means you're telling the model, this is the character that's supposed to be predicted for the current time step, take it. That makes the model learn nothing, right? You're saying this is the character that was drawn at the previous time step, and the ground truth corresponding to that is this. Use that to learn what to predict next, right? Yes. So if it's lesser than that probability, you use the ground truth embedding. Otherwise, you use the embedding of the predicted character. Again, this PO of 1 is going to be what you use to draw. In this case, it'll be if it's a greedy draw, it's just going to be argmax of that distribution that you get at that time step. That tells you what the predicted character should be. Right. That's basically what teacher forcing is. Are there any other sections that you guys have doubts with?
You would also be wondering that if teacher forcing is really performing well, then why don't we use it at inference? Like, does anyone has an answer to that question? So we can't really perform teacher forcing at the time of inference because we don't really have the ground truth, right?
Yeah.
So that's why we are kind of, yeah, exactly. We don't have the answer for the test set. So that's why we can't really perform teacher forcing, but it kind of gives us a way for the model to like learn faster.
Yeah. Anyway, let's go to the actual attention pseudocode here. As you can see, we have projections for each query key and value. The reason we have this, right, set key value function is because the keys and values are going to be the same, right? No matter what decoding time step you're at, right? You're going to be looping over all the time steps and then trying to decode characters at each time step, right? But the keys and values, they're going to be the same because they're obtained from the encoder outputs, right? Which are unique from what the decoder is trying to do, right? So we just have to set the keys and values once. And if you set the keys and values just once, you just have to call it basically before you start the decoding process, and you should be good. We ask you to do that basically here. So before you even start or call the speller, we ask you to set the key and value right here using the encoder outputs that you get from the encoder. Then okay, sure. The set key value function, the reason we have this is because before we do the decoding process, we first send our speech to the encoder, right? And when we do that, we get some encoder outputs. The keys and values are computed from the encoder outputs, right? Because the query comes from the decoder, like Varun explained, and the keys and values are related to the speech. We want to see at a specific time step what portion of the speech to attend to based on the query and key, and then use that to find out what values to pay attention to, right? So we don't have to create keys and values again and again for every decoding time step, because every decoding time step gives us a unique query for that time step. But a query still refers to all portions of speech. It doesn't refer to just one portion of speech for that time step. So you just have to compute the keys and values for all time steps that you get from the encoder outputs just once, and then basically call the attender module to compute the context for every time step using the keys and values that were computed, before you even started the decoding process. Otherwise, it's a waste of, it's basically an efficiency thing. There's nothing wrong with computing it again and again, but you're wasting your computation if you're doing it again and again for all decoding time steps, because technically it doesn't make a difference. Does that make sense, Raghav?
Yeah, it's basically like pre-computing the keys.
Yes, it just does the projection. Exactly. That's all it does. You're just projecting the encoder outputs in basically with a key matrix and a value matrix, right? Value weights matrix.
In the pseudocode, we have just written key is equal to K, like KW, like we have just made the projections, but we have not stored them somewhere.
Yes. So remember, you have to,
yeah. So
you have to remember to store these.
Yeah,
that's correct. You just can't call it key value and then just leave it there. You have to use your self method from your class. So remember those things. So right here, you can see that the query gets projected. You get this from the decoder, right? And then the raw weights. This is basically the inner product between your query groups. This is the inner product between your query and key, right? So you can use either torch.back multiply or einsum to do it, right? Either way, either approach works. When you're doing it, think about the shapes, basically. One is batch size times step projection size. One is batch size projection size, right? And your attention weights should be batch size times time steps, because you want to understand what are the probabilities or the soft, like the raw scores for every single time step, right? So the attention is going to be batch size, time steps, and then your attention context is going to be batch size, projection size. So you want to basically use that knowledge to understand what axes to do your multiplication in, or how to construct your einsum string. So yeah, just try to line the shapes up and then you'll basically understand what to do. And obviously keep the equations from the write up when you're doing that. That's basically all attention's about. You compute the weights, raw weights. The attention weights is obviously this softmax of these raw weights, right? Because you want probabilities. You want to understand between 0 and 1, how much importance does time step t take, right?
and
Yes.
also softmax will happen for each batch. So here you will be like computing these attention weights for like the whole batch of the queries.
Yeah.
Right. So the softmax will only be on like a single dimension, which will be like the last axis. So you'll have to
Yes.
keep all those things in mind.
Yeah. Yeah. Remember, basically pay attention to the shapes and the dimensions here while you're computing your attention and context, weights and context. Same here. The context is, again, you're using the attention weights with the values. Remember that. That's the equation. Speller. So yeah, we're down here. We have really useful diagrams here for you to refer to understand this whole process, the forward process that we've given you right here, right? So as you can see for time step 0, you have the input embedding, which is the embedding of the character at the first time step, right? You need an embedding layer like you do in Homework 4 P1, so that you can basically convert your character into like some numbers that the model can understand in a specific dimension, right? So you have an embedding right here, then an initial context, right? The reason we do this is because at each time step, remember, it draws a specific character from the probability distribution we predicted at the previous time step, and we use the context that we get from the attention, right? So that's kind of why we use the input embedding concatenated with the context as our input to our LSTM, if that makes sense. So this kind of tells the model, okay, this is supposed to be the predicted character from the last time step, and here's the context we get from the last time step. Use both of those together as input to now understand what the next predicted character should be, right? And while we're doing that, we get the context for the current time step, which is natural, right? So we're trying to make use of information like in a sophisticated way. It's not just something that's straightforward, or just use the input embedding, pass it to your LSTM. You're going to have to concatenate your embedding and the context. And you might ask, what is the initial context, right? Initial context, you have a few ways of implementing it. We've outlined it in the write-up. You can start with just zeros if you want. You can start with the mean of the values that you have. You could start with the first value. These are just some strategies that people typically follow. There's no one strategy that's supposed to work really great, or there's no reasoning behind why one specific strategy is just better. It's just convention. It's up to you what you choose. Input embedding, initial context, right? LSTM cells, obviously, that's LSTM cells. How many LSTM cells do you recommend? Start with 2, right? If you feel like you're not getting enough performance, try a deeper LSTM, maybe try 3, right? Remember, LSTM cells increase training time, right? So you have to understand, and it also obviously means you have a tendency to overfit the more deeper your model is. So you have to think about regularization at that point and things like that. But start with 2. That would be my tip.
Yeah. When Vish says start with 2, he means that start with 2 and make your model converge.
Yeah.
If your model is not converging with 2, there's a high chance it won't converge with 3 as well.
Exactly. That's a good point to make. If it doesn't converge with 2, it doesn't mean, oh, my model is just not learning anything, so it has less parameters, let's increase it. That's not the strategy. First things first, your model should be able to converge with the 2-layer LSTM in your speller. So
in this specific homework, we suggest you to not use any kind of regularization until and unless you see the first light of convergence, which basically means that we want you to understand if your model is actually working correctly, right? And that's why we are not using regularization until and unless we get that first convergence. So that's why you keep your model small, and even like a small model will converge if written correctly. So once the model starts converging, then you can apply all the regularizations and start increasing the parameters to get it to converge better.
Yeah, again, small doesn't mean really small, just make it reasonable, right?
Yeah, we have given the initial parameters, and the initial parameters are good.
Around how many epochs should converge in 100?
So
what do you mean by that? Empirically converge in 100?
No, not 100 epochs. We have given a post at Piazza, on Piazza, that talks about the attention diagonals and the convergence. It goes over that you will see, what we mean by convergence is that it's kind of getting a validation distance that is less than 100. So if you start with an initial distance of 300 and 500, it means that it is not converged yet. And you'll see that after 6 to 15 epochs based on your model, it will start converging to a validation distance of less than around 100. So if it's converging, it means that your model is correct. Even if it's like 90 or 60, it doesn't matter. But once you see that convergence, you can start improving your model. And we also suggest that if your model doesn't converge in 20 epochs, it basically means that something is going wrong. So the model will not actually converge until 6 to 7 epochs of training.
You will always need teacher forcing. It doesn't matter what happens. If you want to converge relatively quickly, we recommend it's a must. Use teacher forcing and keep teacher forcing 1, right? And get your attention diagonal, get a distance of less than 100. That means your model is working. Then you can think about what else you can vary. Can we test this convergence? Yes, you can, right? At least you can ensure that your code is working correctly and your attention is working correctly on the toy data set. Yes. Again, the toy data set doesn't directly translate to the main data set. That's something that you need to know. So the toy data set is primarily to ensure that your attention mechanism is correct. You're getting the attention diagonal. Okay, your attention code, there's nothing, no problem with it, right? That's the biggest thing that you have to worry about in this homework, because a lot of it is coming from homework 4P1. A lot of this is coming from homework 3P2. So the one thing you have to worry about is this a lot. You have to make sure this is correct. So, and then some of this that's not from homework 4P1, that should also be correct. So anyway, let me go over this once. So these are just the initializations right here, the max time steps. So why do we say max time steps? Now you're confusing me. Like, Vish, what are you saying? Aren't we supposed to like generate until we get EOS, right? Obviously, you're going to do the decoding and break when you find an EOS. But when you're actually generating tokens, you're going to do it for a certain number of time steps. And then when you're decoding separately, you decide where to stop or where to cut off your decoding, right? You could do it right here, but the problem is doing it for a batch is difficult, right? If you're doing it with a batch size of 1, you could technically go over every single sequence and you can stop when you generate EOS, right? When you're working with batches, instead, you just generate for a fixed number of time steps, and we recommended a specific number in the write-up, I believe, but it's around 600 something. But basically generate for that many time steps. Yeah, 550. There we go. So 550. And you basically generate that because the test sequences, we don't expect it to be longer than that. So generate it for that many time steps, and then you can basically decode afterwards and cut off the sequences wherever they end with EOS in your inference step on your decoding function. Anyway, right here, so the embedding layer is basically converting your characters to a specific latent space. LSTM cells, sequential LSTM cells, output to character here. So this is basically an intermediate layer to ensure that basically whatever dimensions that you have in your character probability can be tied to your embedding layer. Okay, that's why we have this. The reason we have this, because for weight tying, as you might notice in homework 4P1, it basically makes your embedding layer and your classification layer share the same matrix, weight matrix. If you have to do that, that means they're supposed to have the same dimensions, right? But as you can see from this diagram right here, right, your output of your LSTM cell, right, the hidden state and the attention context is concatenated together, right? It's concatenated together, and then it's passed to your CDN. The embedding layer, right? The embedding layer that you have, it's going to go from vocab size, whatever vocab size, to embedding size, right? This, but now has a vector that's hidden state plus attention context together size. That's not going to be the same size as your embedding size. So you have to basically have an intermediate layer that converts that hidden state size plus context size to embedding size, so that you can go back with your character probability layer from embedding size to vocab size. That way you can equate the matrices correctly when you're doing weight tying. Did that make sense? That might have been a lot. I'll repeat it if that didn't make sense. Okay. I'm assuming that's okay, but let's move on to the next. This is the activation. You can use an activation function. You needn't use one. It's up to you. This is again the classification layer going from embedding size to vocab size. If you aren't using weight tying, you don't need to have this layer, but using weight tying is a good form of regularization, so we recommend it. LSTM steps, this is again, you might have seen this in the write-up. This basically goes over your LSTM cells and does computation. Look at the documentation for LSTM cell to understand what outputs it returns and what inputs it takes, right? It's different from your LSTM layer that you did in homework 3. You would be doing this naturally if you went through homework 4. We recommend you to do that there as well. Again, the CDN, this is just asking you to basically elaborate on this block in this diagram. It's going to take in, this is input, hidden state and attention context concatenated. That tensor is input, and is going to pass through the output to character layer, activation, and then the character probability layer. That's what CDN is going to do. The forward right here, this is the the biggest giant in the whole homework that you might struggle to implement or like struggle with. Right here, you have the initial context. You have your output symbol that we call it output symbol, right? And the reason we call it output symbol right here is because you draw the output symbol at every time step to pass its input to the next time step, right? So because you can't have so many variables right here every time when you take the embedding, we've called this output symbol, but technically this is going to be SOS that you're passing as input to your model. So we're sorry for the confusion if this causes some confusion when you're reading it, but output symbol is basically what you draw to send as input to the next time step. For the first time step, it's a special case where you have to initialize it as SOS. Okay. Raw outputs, attention block, is just list to store the outputs that you'll be returning. So if Y is none, why do we have this case? Because we might not be uh, training, we might be testing, right? In which case you might not have the ground truth with transcripts Y, right? In that case, you're basically using self.max time steps. Teacher forcing ratio is 0. Why 0? Because we're testing, right? Don't pass in Y when you're doing validation. Again, just so because what happens is like some people might do this, they might get a distance that is lower than intended in their validation distance. And when you upload it to Kaggle, your test distance might be higher than what you might expect because you've been passing Y during your validation step and your model's just been using that for inference in some fashion. So don't pass in Y when you're doing validation. Remember that. Else time steps. Yeah. How many time steps are we predicting for? Use Y to figure it out, right? Hidden states list. Again, this is just going to be a list similar to homework. We want just a list of nuns. And the reason for that is because we're trying to store the hidden state from every time step and use it for the next time step. Because the LSTM also needs hidden state propagation, right, across each time step. Right here is the logic for teacher forcing. We're looping over the time steps. You're generating a number between 0 and 1. You can use the random library or NumPy or Torch, whatever you want to generate this random number. You check if it's less than teacher forcing ratio and t equals 0. Why do you think it's t? Why do we consider this situation when t greater than 0? Because at t equal to 0, we pass an SOS. Remember that, right? So for time steps after that is when we start teacher forcing, okay? So in that case, when we want to do teacher forcing, the output symbol, or basically the symbol that goes concatenated with the context as input to the LSTM cells, is going to be taken from Y. The character is going to be taken from the ground truth, right? So here, again, you're working with embeddings of characters. So remember to take the embedding of that specific time step from Y, right? Not just Y. That makes sense. Y is going to be, a list of indices. Character embedding right here, basically that embeds the character symbol. Basically, I take Y and then embed it right here. That's what you're doing. LSTM input, like we show here, you want to concatenate it, input embedding in initial context. Concatenated, you can use torch.cat for that. And this is LSTM step. You know the function right here. You kind of have to understand what it returns and what it takes in as input. Attention context and attention weights. This is the part that's important. You're using the attention object that you get from your sequence to sequence model, right? And you're calling this compute context method. What does it take as input? It takes in the decoder context right here. What is the decoder context, right? The decoder context is what you get as output from your LSTM step, right? So remember that. Yeah, what do we retrieve from forward time step to prepare for the next time step? Again, remember this. Hidden states gets passed to the attention module with the keys and values that computes the context. So that should give you a hint on what is decoder context that you have to feed. CDN input, again, we want to concatenate hidden state and attention context, right? That gives us a CDN input. Raw prediction, again, is just what we get from the CDN function. The output symbol right here is going to be what you're drawing from that distribution, from character distribution network. Use a simple argmax. Don't use beam search when you're trying to get things to work. worry about beam search after you get convergence and a good score. You append your predictions and you append your attention weights, right? Then you stack them. Why do we stack them? Because we're doing this for every single time step. You want to stack it so that you have a tensor for all the time steps. LAS is your sequence to sequence model. I think I've explained this already pretty much. You get the encoder outputs, you set the keys and values, and then you call the speller. That's as straightforward as it gets. Yeah. We've given you the baseline configuration values right here, what hidden dimensions LAS uses, what projection size they use. You can feel free to experiment with this, but this is what the baseline uses. This stuff is all the same that you've seen before. Calc edit distance is similar to what you did in homework 3, right? This is basically a different version of your decode prediction function. You don't have CTC decode right here, but you just have to convert your indices to characters. Train function, validation function, all these things are just standard. This is a function to help you plot your attention weights. Make sure you call it right here, right? And when you're calling it, obviously, you want to call it for a single item in the batch, right? Attention plot. You can plot it for a single item in the batch, which is why we do attention plot of 0. You can do it for any item in the batch, doesn't matter, but we just do it for the first item in the batch naturally. But yeah, plot that so that you can understand what your attention maps look like. And yeah, this homework will take a lot of time. We recommend you save your checkpoints, very important. You don't want to train for a while and then lose your checkpoint and then have to retrain again, because this takes time for you to get convergence and for you to like get a good score. So checkpoint, that's extremely important. Make sure your checkpointing method works. Save it in your drive or save it in weights and biases. Make sure you're saving it somewhere. Yeah, that's about it. Just following this around should help you solve this homework. It's a little difficult, has a lot of moving parts. Test it on the toy data set first. Get a diagonal like this, right, on the toy data set. It's a simple diagonal. It's just, small sequences. Get the diagonal like this on the toy data set. And when you're working with the toy data set, we also tell you in this function, calculate distance right here, right? Follow these comments. Comment the above and then comment the below for the toy data set. Why? Because we're working with lists of phonemes, so we don't want to create a string there. We instead just work with the slices, the list. Similarly, right here, instead, you want to print white sliced and red sliced if you want to be working with the toy data set. So yeah, go through the code. Don't just try to blindly run things. If you have any doubts, feel free to come to office hours or ask us on Piazza. I think that's about it. Do we have anything else to cover?
No, I think that was pretty comprehensive.
Yeah.
I think this has already been like a longest boot camp for any
Yeah.
of. Yes, but I think that will solve a lot of questions people have. And
yeah, the goal was to basically solve questions. If you still have questions, feel free to ask us on Piazza, right? But yeah, this is a difficult homework, but keep asking questions. We'll help you guys out. And start early. Yes, please start as soon as possible. So there's a lot of moving parts. Homework for P1 is easier to finish. We recommend you finish that first at like whatever happens, finish that first, but try to finish that quick and get to this, right? So that's the point. Yeah, all the best. And I think I wish you guys good luck. This is the last one. Trying times, it's going to be stressful, but we'll help you guys out as much as we can.
yes, all the best, guys.
Yep. See ya. Bye-bye.
I just want to confirm one small
Yeah.
thing. With that early quiz, so like the previous homeworks did, again, I'm just confirming because I think I read this on Piazza. Like the earlier things, we had to give a quiz as well as early submission to get that 10%. But for
Yeah.
this homework, we don't have to do that for 10%. It's just a
Yeah.
bonus 10%, right?
Yeah, basically, yes. You have to get the Kaggle cutoff though, right? You have to submit the quiz and you have to get the Kaggle cutoff by the early submission date for you to get the bonus points. How
Yeah.
much exactly? I'm not sure if it's going to be 10 points or what it is. It'll be like the professor will decide that, but the bonus points that you get will be if you finish both the quiz and the cutoff.
All right. Thank you.
Yep.